All right, morning everybody. So, hope everybody had a good Friday. Today we're going to get into chapter 18. We're going to start talking about carbonyl compounds, but we're going to start talking about doing things at the alpha carbon, not at the carbonyl carbon. And so when we were learning about the carbonyl carbon, what kind of chemistry did it do? Okay, so it participated in nucleophilic reactions, but was it the nucleophile or the electrophile? It was the electrophile, right? So we were adding things to the carbonyl. So what could we do? Let's refresh. We could add Grignards and make alcohols. What else could we do? Yeah, we could turn them into carboxylic ester derivatives, right? If we had carboxylic acids, we could do that. What else could we do? Yep, we can make acid chlorides. What else could we do? So if I had a ketone, what can I do to a ketone? We just talked about being able to add Grignards. What else can we do to it? Pardon? Yeah, we can either make an alcohol by addition of a Grignard or through a reducing agent. What were the reducing agents? LAH, sodium borohydride. What else can we do?
Convert it to an amine.
Pardon?
We can convert it to an amine.
Yeah, we can. What else can we do? What if we wanted to protect the ketone? What would we convert it to?
Acetal.
We can convert it to an acetal. So there are a lot of things that we could do to a carbon-oxygen double bond, right? We can convert them into alcohols. We can make imines. We can make enamines. We can make alcohols. We can make acetals. We can make hemiacetals. In your reading, there was the cyanohydrins, where cyanide is the nucleophile. We could just about do anything we wanted to that carbonyl in terms of breaking that weak pi bond and then doing other things with it, right? And so now we're actually going to switch things around a little bit. And we're not going to be talking about the carbonyl carbons per se. We're going to be talking about the carbon atom directly attached to it. And it turns out that the chemistry is exactly the opposite. Where carbonyl carbons behave as electrophiles, the alpha carbon will behave as a nucleophile. And so we're going to talk about different types of chemistry with that. So we're going to talk about things that we can do with the alpha carbon. We're going to talk about making enols and enolates from those alpha carbons, okay? And so we'll talk about a variety of different reactions. It turns out that the alpha carbon of a carbonyl is a very powerful position that allows us to do a lot of different types of chemistry. Okay, we've already talked a little bit about enols at various points, right? We know what an enol is, right? It's just an ene with an OH attached to it. We can get this from, in this case, it looks like we've got a ketone, right? What kind of process is this, going from here to here? It's tautomerization, right? And that hydrogen is moving and the pi bond is moving. It's a keto-enol tautomerization. Does the equilibrium lie to the enol or to the ketone? Ketone, right? Is that what you said? Okay, I'm sorry. I thought I heard you say enol. It lies to the ketone. The enol is not favored, right? But it can be formed. And it turns out that these are good nucleophiles, okay? And they will react with electrophiles to make a new carbon electrophile bond at the alpha carbon. So we can actually replace one of the hydrogens on the alpha carbon with some electrophile. So what might that electrophile be? Pardon? Halogen. It could be halogen. It could be another carbon, if that carbon has a leaving group on it, right? So we can make carbon-carbon bonds. In theory, it can be. Yeah, there are reagents that we're not going to get too much into that in this class. But yeah, it could be. It could be just about any electrophile you want. Okay? And it turns out that the alpha carbon is the carbon that behaves as the nucleophile. Okay? We also have the ability to generate enolates. How does an enolate differ from an enol? How does it differ? Okay, it's got a negative charge on the alpha carbon. That hydrogen is really gone, isn't it? Is that the only resonance structure I can draw for that enolate? How else can I draw a resonance structure?
You move the pipe.
I can move that, right? So I can move this here, break the weak pi bond, and put the negative charge on oxygen, and have that. And that is actually the major contributor to the resonance structure of an enolate, okay, because the negative charge is on oxygen. However, electrophiles almost always react with the carbon. In theory, they could react with the oxygen. And there are some electrophiles that react with oxygen of enolates. And that is actually a topic for a higher level chemistry course where you try to figure out which nucleophilic atom. But for the most part, it's the carbon atom of the enolate that behaves as the nucleophile. Okay? So let's take an example. So we just determined that the ketone is favored at equilibrium. So if we take cyclohexanone and we place it into solution, we're going to get about less than 1% of the enol form, okay, going through this tautomerization. Okay? It is not favored. However, that does not mean it's not important, right? Small concentrations of things can do big chemistry. This is a symmetrical ketone, and so the two alpha carbons are the same. Regardless of which hydrogen tautomerizes, you get the same enol. However, we can have an unsymmetrical ketone, and we have to take this into account. So we can have tautomerization at the alpha carbon here on the right, or the alpha carbon here on the left. And when we look at this mixture, we recognize that the total amount of carbonyl that has gone to form the enol is less than 1%. However, which one of these enols is the major one of this less than 1%? The one on the left or the one on the right? The one on the right. And why? It's the more substituted double bond. That's right. So this is the, if you could see the enol, this would be by, the vast majority of that enol material. Okay. Now there are some molecules that prefer the enol compared to what we just talked about. Typical ketones, less than 1%. Typical aldehydes, maybe a couple percent. But these are not typical ketones. Okay, this is a beta dicarbonyl compound. Alpha, beta. Alpha, beta. So it's beta dicarbonyl. What do we know about these hydrogens? More acidic or less acidic than a typical carbonyl? They're more acidic, and why? Okay. What else?
They readily donate protons, and then the negative charge on carbon can be delocalized.
Okay, that's true. They're more acidic. When you have the conjugate base, it's delocalized over 2 carbonyls as opposed to just 1. And these types of diketones, if you will, they really do like to tautomerize. And you'll find that about 75, 76% of this compound will exist as the enol form. Okay? So the enol here is actually a bit more stable than the dicarbonyl. Can you explain to me why the enol in this case is more stable than the carbonyl? Part of the answer is up there.
Hydrogen bonding.
There's hydrogen bonding. We've got a 6-membered ring. Anytime we form bonds, that's a good thing. And what else? And conjugation. Are these pi systems in conjugation with one another? Not at all. Are they now? We have a conjugated system. We can draw resonance structures here and here, right? And so it actually exists, for the most part, as this enol set of tautomers. So if I gave you 2,4-pentane dione and I told you to go down and run an NMR, what you would find is that by looking at these protons, you'd find that about 24% of it, or let's just call it 25%, is in this form. And you would see a new proton for this. Okay, and you would be able to actually detect that by NMR, and you would see that about 3/4 of the material is actually this. Where would we expect these protons to be in the NMR spectrum? Those alpha hydrogens, where might you expect them to be? What range? What's their hybridization? They're sp3, right? So where might we expect them to be? Pardon?
Like the 2 to 3 range.
Yeah, somewhere in that ballpark. Maybe a little further down because there's 2 ketones. But yeah, somewhere in that ballpark. And where would we expect this proton to appear? What's the hybridization now? sp2. So where might we expect that to appear?
Greater than 5. It's like
Somewhere between 5 and 6, maybe. Yeah, that's not a bad guess, right? And so we have 2 distinct places that we'll be able to look and see the signals for these molecules and be able to get integrations and determine what the ratios are. Okay? So there are some molecules that favor enolization. There are some molecules that do not favor enolization. So normal aldehydes and ketones, it's the keto or aldehyde form that's going to be the majority of your material. But when you have these beta dicarbonyls, most of it's going to be as an enol. Okay? And because you get this additional hydrogen bonding and you get this conjugated system that actually stabilizes the enol relative to the dicarbonyl. Okay? So let's look at a way in which we can form an enol in both acid and base. Turns out that you can form enols and acids, and you can form enols under basic conditions. So let's take just some generic ketone, and we're going to place this in some medium, and we're going to get an enol. Okay? Let's say we're under acidic conditions. Got a little bit of acid around. How's this going to help us form an enol? What would be the first step of that mechanism?
protonating the oxygen.
Okay, we're going to protonate the oxygen. That's the only Lewis basic site we have, right? So we're going to protonate the oxygen. Now I'm just going to use normal equilibrium arrows. And I'm going to draw out one of those hydrogens explicitly. What am I missing?
The formal charge on oxygen.
I've got a formal charge on oxygen, right? Now we know that H plus has to have some counter ion, right? So I've got some counter ion around. Now what happens?
Counter comes back to the proton on the left.
And now help me push the arrows. Now what happens?
Then that bond makes an alkene, or it makes a pi bond, and then you push the carbonyl pi bond up.
Okay. So we started with HX, we ended up with HX, so this must be catalytic, right? We can catalytically form an enol in the presence of acid, okay? And it turns out you don't need much acid at all for this to occur very well. Now, let's say you have just a little bit of sodium hydroxide and you've got water. So you're putting in sodium hydroxide and water, it's going to form an enol. How does that happen?
Base pulls back the alpha hydrogen.
Okay. So let's just draw that out a little better. Now what happens?
The oxygen gets protonated.
By what?
Water.
And so we then generate the enol plus hydroxide, meaning that this is what? It's catalytic and hydroxide. So under sodium hydroxide, potassium hydroxide, or HCl or HBr. We can generate these enols under these conditions, both under acidic and basic conditions. Okay? And so it turns out that these hydrogens are not acidic enough for hydroxide to really abstract the proton, and so you end up with enols, not enolates. Enolates would require a much stronger base, and we'll talk about that as we move forward. Any questions about the mechanism for forming? One of my favorite questions on the next exam is, given a series of carbonyl compounds, which one's most likely to form an enol, or forms the greatest amount of enol, or something like that? So you need to understand the factors that go into formation of enols. You need to know the mechanism. You need to know what stabilizes an enol. You need to know what favors enolization. Okay? So that's important for you all to know. All right. Enolates are not enols, but they have very similar chemistry. They actually are negatively charged species. Okay, you have a negatively charged oxygen atom in an enolate. And they are formed by a base reacting at the alpha carbon, removing one of the acidic alpha hydrogens, and then the resonance structures. Okay? It is a resonance stabilized enolate anion. Okay? So here, what kind of base might I need? Is hydroxide going to be good enough? No, because hydroxide will form an enol, right? So what do I need? Do I need something stronger or weaker than hydroxide? I need something stronger than hydroxide. And what were some of the bases that you've learned so far that are stronger than hydroxide? Lithium aluminum hydride is going to function as a reducing agent, not as a base. Butyl lithium. Okay, butyl lithium is certainly stronger. But what's the problem with butyl lithium? If I reacted this with butyl lithium, would it pull off the alpha proton? I thought Grignards and lithium reagents would attack a carbonyl and make alcohols, right? That's what's going to happen. So what's the deal? Butyl lithium is certainly a much stronger base than hydroxide. It's about 50. So why does it not form an enolate? Instead, it would form an alcohol after it was all worked up. Why would butyl lithium go after the carbon of the carbonyl and not the hydrogen? It's very nucleophilic. They're very strong nucleophiles, right? So what do I need? I need a strong base that is not a nucleophile, right? And so we learned that all nucleophiles are, but not all Lewis bases are nucleophiles, okay? And that's a problem here. I've got these two functional groups in this molecule. I've got the alpha hydrogen, and I've got the electrophilic carbonyl carbon. If I'm using a base that's highly nucleophilic, I'm going to have it behave as a nucleophile and just break the weak pi bond. I need a base that is non-nucleophilic. So what were some non-nucleophilic bases that we learned about? Potassium terbutoxide. Is it a stronger base than hydroxide? Yeah, but only slightly. It has a pK of around 19. Hydroxide's pK is around 16, right? So, well, that's a few orders of magnitude. So it will do the job. What other bases have we learned about that were strong non-nucleophilic? They were initials. Huh? NBS is N-bromosuccinimide, not a base. DBU and DBN. Okay, those were non-nucleophilic bases. Not strong enough, however, to make substantial quantities of enolates. So we're going to learn about another base at some point here called LDA. Organic chemistry tends to happen in three-letter acronyms. DBU, DBN, NBS, LDA. Okay? And LDA stands for lithium diisopropyl amide. And it is a strong non-nucleophilic base that can actually promote the formation of enolates from ketones and aldehydes quite nicely. Okay? So, PKAs are going to haunt you for the rest of the semester. They're going to haunt you when you get into biochem. So you might as well get used to it now, right? And you need to know these rough ranges, right? I don't care that you know exactly 4.8 or 4.75 or 16 exactly, but you should have a feel for these ranges. So for example, we know that an alkane has a pKa of around 50, right? Butyllithium, for example, that's not butyllithium, but I mean, has a pKa of around 50 because it's just an alkane with a negative charge on it, right? We know that if we can add some resonance, that lowers the pKa value, makes those hydrogens more acidic. So the hydrogens on this carbon, right, can be removed a lot easier, and so their pKa is around 43, and that's because we can draw resonance structures. What's the name of this carbon bearing the negative charge? Well, it is a carbanion, but it's a specific type of carbanion. Not vinyl. Vinyl is when it's directly attached to the C double bond C, when the negative charge is there. So this is the one adjacent to the carbon-carbon double bond. Allylic, right? These are allylic hydrogens. They have a pKa of around 43. Here's a good ketone. This is acetone. Ladies, this is your fingernail polish remover, right? It has a pKa of about 19. Okay? So if you take acetone and you use a strong enough base, you can generate an enolate from that. It has a pKa of about 19. In terms of organic molecules, that's fairly acidic, right? It's certainly not a strong acid by any stretch of the imagination, but it's a pretty good acid for us, right? So we can remove these hydrogens under fairly easy conditions and make enolates, okay? Alcohols, pKa is around 16. Carboxylic acid's around 4.5, 4.75, somewhere around that ballpark. Okay, so they put 4.8. You need to have an idea for these pKa's. Now, if we take a carbonyl and we start adding things onto it, that can either raise the pKa or lower the pKa, right? So what could we do to this ketone to actually lower the pKa? Would we add electron donating groups or electron withdrawing groups? Okay, so if I add an electron donating group to this molecule, is that going to stabilize the anion or destabilize the anion? Destabilize. I got to stabilize this, right? So how am I going to stabilize something that's negatively charged? I want to use electron withdrawing groups. So if I put things out here that are electronegative, I'm going to lower the pKa, right? So we'll talk a little bit about that as well. You need to have a feel for this. You're not going to have that note card on exam 3. Right? You've got to have these pKa ranges down. Okay? We can also generate enolates not only from carbonyls being aldehydes or ketones, but we can also generate enolates from other carbonyl containing molecules. So for example, esters will also generate enolates. You can generate enolates of esters. Believe it or not, you can generate enolates from carboxylic acids. You just have to generate, you just have to use 2 equivalents of base, one to remove the acidic hydrogen and the other one to remove an alpha proton. We can also remove the hydrogens from nitriles. That's not a carbonyl, but remember it belongs in the same family because of the oxidation state of that carbon. The pKa's of these hydrogens are about 25. Now wait a second, we just said that a ketone is about 19. Why would an ester all of a sudden go up to 25? Other than the fact that somebody sat there and titrated this and figured it out, why would an ester have such a much higher, that's nearly 6 orders of magnitude difference in acidity. Why would an ester be less acidic than a ketone or an aldehyde?
Because they're electron donating groups on it?
That's right. This oxygen atom actually donates into the carbonyl, remember? And so it makes this system less likely to accept a pair of electrons from the alpha carbon. That's the easy way to think about it. Okay? So esters are less acidic than ketones. Ketones are actually less acidic than aldehydes. Okay? Nitriles are about the same acidity as an ester. Okay, so we have these resonance stabilized systems. We can also have amides. pKa's are going to be, a little bit higher than you would have for an ester. So here we go again, another list of pKa's, right? So the alpha hydrogens on the alpha carbon, we're not talking about any hydrogens on the nitrogen here, okay? We're just talking about the alpha carbon. For an amide, it's about 30. A nitrile about 25, an ester about 25. A ketone about 9. What are we seeing here in terms of the trend? As we go from this functional group to this functional group to this functional group. What are we kind of seeing? We're seeing about more or less 5 pKa units, right? So that's an easy way for you to remember this. Just remember, amides are around 30. Esters and nitriles are about 5 below that. And then ketones and aldehydes, more or less, are about 5 below that. This is kind of a rough range. It kind of gives you an idea of how to figure out where your pKa ranges are. So what do you have to remember? You have to remember the pKa of the alpha hydrogens of a tertiary amide. They're about 30. Then you just go down to 25. You put the next set of functional groups. You go down about 5 more there, and you have the next set of functional groups. Okay? And so that works pretty well. So aldehydes, esters, nitriles, and amides, you can kind of figure that out by remembering that trend. Now, all of these are going to require relatively strong bases to completely generate the enolate. We're going to have bases that are higher in pKa than what we have here, right? And those are pretty strong bases, because we said that hydroxide's around 16. However, when we start doing this other business of putting more than one functional group on an alpha carbon, things change. Notice that a 1,3-diester, for example, okay? These hydrogens are much more acidic than the hydrogen for an ester over here. Here they were about 25, right? Over here they're around 13. What can I use to deprotonate that ester now? Those alpha hydrogens.
Hydroxide.
Something like hydroxide. Turns out hydroxide doesn't work very well because it's not soluble in an organic solvent, but alkoxides are about like hydroxide, right? And so you could use alkoxides like sodium methoxide or sodium ethoxide to deprotonate those hydrogens. The 1,3-dinitrile, 11. The beta keto ester, so we have a ketone and an ester, about 11. And a beta diketone, under 9. Those hydrogens are getting, for an organic chemist, quite acidic. Okay? We would expect these things to lose their protons quite easily and form enolates very, very easily. So I'm not going to need as strong a base. Over here, I'm going to need a strong base to do the chemistry that I want to do. Over here, I can get away with something much less strong. Okay? Again, spend some time. Put this on your flashcards. However you study, you need to know these pKa ranges. They will appear on the next exam. And you know me, I'm not going to have a question that just says, eliminate 4 that are just, or 3 that are just ridiculous. But you need to kind of know these rough ranges. Okay? So, if we look at the reaction of a ketone, okay, and here they're talking about just a typical ketone. We don't know what the R group is here. We know the pK is going to be around 20, and there's our enolate, right? And so we want to drive that equilibrium to the right. We want to generate an enolate so that we can do chemistry with it, right? And so we need to figure out what a good base would be for that. Now, if we do a little bit of math that I'm not going to ask you to do, if we were to take that ketone and react it with sodium hydroxide, we would generate less than 1% of the enolate. Is that going to be efficient? Not at all. If I used an alkoxide, again, alkoxides have similar pKa's to hydroxide, we expect a similar result. Okay? Potassium tert-butoxide, as Jack said, actually has a much higher, not much higher, but a significantly higher pKa than hydroxide. It's around 18. Okay? And so we're going to start getting anywhere between 1 and 10% of the enolate formed under those conditions with that particular carbonyl compound. But that's not anything to really write home about. However, If I use bases like sodium hydride, okay, remember this hydride actually only functions like a base, not as a reducing agent, right? Hydrogen has a pKa of around 35. 35 is a lot higher in pKa value than 20, and so it's going to push the equilibrium completely to the right. I'm going to generate 100% of my enolate using sodium hydride. Okay? So Ashley comes into the lab and she's got a ketone that she wants to completely convert over to the enolate. She could take that ketone, let's say it's acetone, and she could add it dropwise into a THF solution of sodium hydride, and it would generate the enolate form. Hydrogen gas would be the conjugate acid that's formed, and it would bubble out a solution. It would be very vigorous and potentially flammable. Okay? So she'd have to be careful doing it. But it can be done. There is a other reagent here that we can use called lithium diisopropyl amide. Okay? Lithium diisopropyl amide. Okay, we've got the lithium salt. That's a pretty strong base because diisopropylamine has a pK of around 40. So this is even a stronger base than what we talked about using for sodium hydride. It also has an added benefit. What's the added benefit? Actually, it has two added benefits. What are they? Do you think it's going to be nucleophilic? It is not, and why? Yeah, it's got these big bulky isopropyl groups. So it's not going to be able to function as a nucleophile. It can only function as a base. That's benefit number one. Benefit number two is that it's organic and it's soluble in things like THF. Sodium hydride is not. So it is a soluble, strong, non-nucleophilic base. So how do we make LDA? We start off, we buy this thing called diisopropylamine. That's just an amine. What kind of amine is it? That's a secondary amine. Technically, you can buy LDA, but every time I've ever bought LDA, it's crap. Because it's such a strong base, it slowly reacts with air and things that it comes into contact with. So most chemists that are worth their weight in salt actually make this stuff on demand. Okay? So how do I go from there to there? Diisopropylamine is cheap. I actually spend more getting it shipped to me than the material itself costs. So I buy 100 milliliters of diisopropylamine, probably costs me $20, $30. Shipping it here would cost me about $40. So it's cheap, readily available. How do I convert it into that very useful lithium diisopropyl amide? Or amide, as people like to call it. Spelled the same, they end up saying amide, but they're actually pronounced. What do I need?
You need a stronger base, right?
I need a base. And I need a base that's stronger than what? Okay, so give me a pK range. Well, what's that one? 40. So that I know that my starting material has a pK of 40. I need something that has a stronger pKa than 40. What do we know has a stronger pKa than 40?
Butyllithium.
Butyllithium. And so this is exactly how we make this. You take diisopropylamine, you put it in tetrahydrofuran, which is a polar aprotic solvent. It's not terribly polar, but it's a polar aprotic solvent. And you can dry it, THF. Yeah. We typically cool this down to minus 78 degrees. Then you take a brave soul and you get a syringe full of butyl lithium and you add it to this dropwise. And so what are the byproducts going to be? The lithium obviously comes from here, right? What's my other byproduct? What's a butyl? Butane, exactly right. Butane, and is that a liquid, a gas, a solid? What is butane?
It's a gas, right?
It's a gas and it bubbles out of solution. Which is kind of nice. So what's left behind is pure LDA. Now this is a great trick. Because what would happen, Jack, if we tried to use butyl lithium to deprotonate that carbonyl? It would act as a nucleophile. But when I react butyl lithium first with this, I generate a base that is going to be strong enough to do the chemistry that I want, but it's not going to be a nucleophile. Okay, so I can trick Mother Nature a little bit here. Okay? And so things like lithium diisopropylamide are going to have pKa's that are large enough to drive this reaction completely to the right. And so if I want to generate an enolate completely, I need to use a strong non-nucleophilic base in a polar aprotic solvent. Very important. What would happen if I was to take LDA and react it in a polar protic solvent?
We would just do acid-base chemistry.
We would just do acid-base chemistry with the... Remember when you all were in Gen Chem and you learned about the leveling effect? That was quick. You need to go back and review that. So there's this thing called the solvent leveling effect. Remember in water, no matter how strong the acid is, when you add it to water, you can never have an acid stronger than H3O+. That's the leveling effect. You can't have a base in water that's stronger than hydroxide because of the leveling effect. Same thing happens here. If I take a strong base like LDA and I added it to, let's say, ethanol, it would actually generate an alkoxide. I can't have anything stronger in alcohol than an alkoxide because that's what will happen. That's the leveling effect. So to do this chemistry right, you have to use polar aprotic solvents. So let's review. What were some polar aprotic solvents that we learned about? Obviously THF. What were some others? DMSO. DMSO is great, but it's a pain to work with. It's hard to get rid of it at the end because it's so viscous. What else? Those were the two that I really hit home on. But there were a few others that we learned about. Actually, acetone is a polar aprotic solvent. Would that work here? It would react. That's right. So we got to have polar aprotic solvents that don't do this chemistry. So pretty much do anything without a carbonyl. So you're going to be limited to things like DMSO, THF, ethers, those types of things. Okay? So if we look at the reactions of enolates, we have our ketone, we have the alpha hydrogen, we have a strong non-nucleophilic base, we generate an enolate, and we know that the enolate is in resonance with the negative charge being on carbon or the negative charge being on oxygen. Which one of these enolates structures is the major contributor? The top or the bottom? The bottom, and why?
Negative charge on oxygen.
Negative charge on the electronegative atom, right? And so if the oxygen reacts with the electrophile, we would make a new oxygen electrophile bond. But the carbon atom of the enolate can also react with the electrophile to make a new carbon electrophile bond. And it turns out that the preferred pathway is the top pathway, not the bottom pathway. It's rare to actually do electrophile chemistry on the oxygen atom of an enolate. It can be done, but it is beyond the scope of this course. Explain to me why the top pathway is preferred and the bottom pathway is not. Okay, the carbon-oxygen pi bond is favored. That's part of it. What else? Would carbon with a negative charge be a better or worse nucleophile than oxygen with a negative charge? And why? Oxygen is more electronegative, and so it's holding on to its electrons more or tighter. The carbanion, more willing to share its electrons, right? So it's electronegative. And so even though this is the minor contributor to the overall resonance hybrid, it is the resonance structure that we like to use when we're showing these reactions because it accounts for the chemistry that is occurring. Okay? So, let's suppose we have an unsymmetrical ketone. Here we have an alpha carbon that has a tertiary hydrogen. Here we have an alpha carbon that has a secondary hydrogen. Okay? There are two paths for our base to react. It can remove the secondary hydrogen and generate the less substituted enolate, or it can remove the tertiary hydrogen and generate the more substituted enolate. The top enolate forms faster. Therefore, it's what? It is the kinetic product. It forms the fastest. It forms first. Okay? Why is it faster to remove a secondary hydrogen over a tertiary hydrogen? What's your go-to answer in these kinds of Sterics, right? So if we have lithium diisopropylamide that's bulky, is it going to want to react with a hydrogen that's around a lot of bulk, or is it going to want to react with a hydrogen that's pretty easy to get to? It's pretty easy to get to, right? And so this is actually the enolate that is formed faster, and it's called the kinetic enolate. This, however, generates the more stable enolate, and we call it the thermodynamic, right? And it is the thermodynamic enolate because that carbon-carbon double bond is the more substituted. And we learned early on that carbon-carbon double bonds, the more substituents we have, the more stable the alkene, right? Same process here, okay? So this looks like, to me, this is going to create a problem for us, right? There's two possible ways, two possible enolates that we can get here. Is there any way that we can control whether we get the kinetic or the thermodynamic? Temperature is one great way to do that. At really, really low temperature, which enolate's going to form? The kinetic. At higher temperature, what one is going to form? Thermodynamic. That's exactly right. So we can control whether or not we have kinetic enolates or thermodynamic enolates. And it actually turns out that there's more to it than just temperature. Okay? If I want a kinetic enolate, I need to do it really cold. I need to use a very strong non-nucleophilic base, and I need to use a polar aprotic solvent. If I want to generate the thermodynamic enolate, I can do higher temperature and a weaker base. I can also generate them in polar aprotic solvents. I might not be able to generate them to complete 100%, but they're going to be the thing that is allowed to form. Okay? So we can actually look at it that way as well. Okay. So you need to know this. The kinetic enolate is favored by a strong non-nucleophilic base. For your purposes, that go-to base is going to be what? LDA. You need a polar aprotic solvent, okay? Because the solvent has to be able to dissolve everything. Everything has to be in solution for this to happen. Yep. So it's going to have to dissolve the base, and it's going to have to dissolve the starting material. And you're going to want to use low temperature. Minus 78 or colder. So if I tell you you did this at minus 10 degrees, that's not cold enough. It'll probably give me a lot of the thermodynamic. We're talking really cold stuff here. Minus 78 will give you frostbite pretty quick, right? And so under these conditions, as long as I keep everything cold, I'm going to generate the kinetic enolate. All right, so you all have 17 inverted lecture to turn in for me today. Go ahead and set that up here on the corner on your way out. We will pick up on this on Wednesday. I will have the sapling up this afternoon. I have not got that up yet, but I do have the slides up on the canvas. And I will see you all later.